Okay, good evening everyone, and welcome to this masterclass on validating RDF with the Shape Constraint Language. My name is Veronika Heimsbakk, and I'm a senior consultant at Capgemini, Norway. I live right outside of Oslo with my fiancé and our two children, three-year-old Edward and one-year-old Oda. I got my degree from the University of Oslo with a specialization in logic and semantics. And a work experience, I've been touching into stuff like writing kernel modules in C to semantic technologies applications in Java. So I started off as a developer, but when I joined Capgemini in 2019, I have been working as a semantics nerd, information architect, and advisor. I've worked in several different industries like oil, life sciences, public data, library, and media. I started working with SHACL in 2016, and yes, that is before it became a standard. And as all nerds, I have way too many hobbies. I enjoy making stuff, hunting, board games, and teaching kids to code, to name a few. So the agenda for this evening is to start off with a traditional lecture, including basic terminology and concepts of semantic technologies. This might be a repetition for many of you. However, I find it important enough to be repeated, as I'll use these terms in my lecture. I'll also compare the more familiar web ontology language with SHACL in order to clarify the similarities and differences between these two technologies. And you will also see the complete SHACL Core constraint vocabulary, including some examples. This is the vocabulary we're going to use for our later hands-on tasks after the lecture. Yes, and after the lecture, we're going to look at some data examples, both instance data and shapes graphs. And then we'll get some hands-on experience by working with the tasks. And at the end, we'll summarize, and I'll go through all answers to the tasks. And if one of you would like to volunteer to show your solutions of the task, that will be great. And as mentioned, if you have any questions during the lecture, please type them in the chat here or at Slack, preferably at Slack, for the moderators to pick up. And we'll go through them at the end of the lecture before we attack the exercises, if there are any questions at that point. Okay, so once upon a time, there was the creation of the World Wide Web. And with it came some standards. And as you know, RDF wasn't created yesterday. And we've been through quite a few graph implementations throughout the years the web has existed. However, semantic graph technologies are rapidly expanding in popularity, as we can see at this conference as well. In 2014, an RDF data shape working group was established, and their result was the Shape Constraint Language, standardized as a W3C recommendation in July of 2017. So let's start off with the terminology needed for talking about semantic data and its languages. The domain and range properties are found in the RDF schema vocabulary. Even though I hope this information is familiar to you all, I'll quickly go through their definitions. The domain of a predicate tells us something about the subject position of a triple where that predicate is present. In this case, author has a domain to book. That means for every triple where author is the predicate, the subject shall be an instance of book. The range of a predicate tells us something about the object position of a triple where that predicate is present. Here we say that author's range shall be an instance of person. So every triple where author is the predicate, the object value shall be an instance of person. And now let's talk about T-boxes and A-boxes. They are, after all, the building blocks of the semantic knowledge graph. And first, the T-box is a term component that describe abstract concepts, and these abstract concepts are sets of individuals. In this example, we have a triple that states book as a subclass of work, and this statement is a term component, a T-box statement. On the other hand, we have ABox statements and a certain component, and the ABox statements describe individuals or elements of a set. They are instances of abstract concepts. In this example, we have the resource The Hobbit as an instance of the concept book. We can think of The Hobbit as an element in the set of all books, and this is an ABox statement. So, T-box and ABox statements combined is what we think of as a semantic knowledge graph. The resources on the top here, where book and movie is both subclasses of the class work, are all T-box statements, combined with the instances of both movie and book and their relationships. The ABoxes make this a pretty little semantic knowledge graph. Next up, the world assumptions. First, I want to talk about the open world assumption. This world assumption admits that it has incomplete knowledge. The web ontology language operates under this world assumption. And it is the assumption that the truth value of a statement may be true, irrespective of whether or not it is known to be true. Let me talk you through an example. Let us assume that everything you know in the entire world is the statement. In a hole in the ground there lived a hobbit. You don't know anything else about the entire world. And someone asks you, do Gandalf live in a hole in the ground? Based on your knowledge of the world in an open world assumption, your answer would be unknown, because you do not have any sufficient knowledge to say whether Gandalf is a hobbit or if he lives in a hole in the ground. On the other hand, we have the closed world assumption. The Shape Constraint Language operates under this world assumption. The closed world assumption says that any statement that is true is known to be true. What is not currently known to be true is false. So, let us revisit our example. Again, let us assume that everything you know in the entire world is the statement. In a hole in the ground there lived a hobbit. And someone asks you, do Gandalf live in a hole in the ground? Based on your knowledge of the world in a closed world assumption, your answer will be no. If you do not have sufficient information in a closed world assumption, the result will always be false. So now we can talk about the Shape Constraint Language. And I'll start off with some history, because prior to SHACL, closed world validation of RDF was performed using SPARQL queries. And as most of us know, complex and large SPARQL queries can be quite messy and readable and time-consuming. It is not for nothing that the S in SPARQL stands for SPARQL. So we needed something else. And if the solution were to be recommended by the W3C, even better. So with the SPARQL inferencing notation and IBM resource shapes as inspiration, the RDF data shape working group started developing a language for schema-based validation of RDF data back in 2014. And that seems like yesterday, don't it? Anyway, it led to the Shape Constraint Language that got recommended by the W3C in 2017. And I will start by showing you an example of a workflow with SHACL in coexistence with OWL. This approach has been adapted at 2 of my previous projects when working with SHACL. And I want to mention the first one. That was a project for the Norwegian Digitalization Agency. And as input, we received all documents produced by public agencies in Norway in some funny Norwegian archive formats. We transformed this to RDF, applied the OWL reasoning before validating with SHACL. And if the graph conformed true, it was stored in a graph database and indexed to Elasticsearch. The end user could then ask for insight in any document stored in the database. And because of the SHACL validation, we could assure for correct data with high integrity. And after all the data in this service was to be delivered to the national archives as well. Anyways, RDF is the shared base technology of both OWL and SHACL, which lets you add statements about RDF URIs. Some statements are interpreted by OWL engines and some by SHACL engines. Any URI can carry various triples for different purposes. A book, for example, may carry both OWL axioms and SHACL constraints. However, best practice would be to store axioms and constraints in different files in order to keep your data organized. Applications may then decide whatever features it needs, whether it's the OWL axioms for inferencing or SHACL constraints for validation. This approach can come in handy as OWL axioms will cover different things than the SHACL constraints. As long as they use the same URIs for T-box data, your ABox data can be used in any context. So before we grasp onto the SHACL core constraints, I want to enlighten you a bit more about the differences between OWL and SHACL. And first of all, the design purpose behind both languages. As I already mentioned, OWL is designed for inferencing in an open world assumption. OWL restrictions describe inferences to be applied. They are not data constraints. Let me talk you through an example of that. So let's say we have OWL max cardinality 1 on a person's nationality. And there is one person in your ABox data that have 2 nationalities. If this was a SHACL constraint on max count 1 on a person's nationality, and there was a person instance in the data that had 2 nationalities, you would get a validation error on it and a validation result that described what kind of violation occurred. An OWL reasoner, on the other hand, will assume that these 2 values represent the same real-world place, even though the URIs for the nationalities are different. And this is also an example of OWL's lack of unique name assumption. So, and if you don't find the constraints you need in the existing SHACL vocabularies, you can always add your own constraints and push them to the web for anyone to reuse if you like. OWL is, however, limited to the features described by the OWL committee. And you cannot match instances to a given schema with OWL or RDFS. You will only get logical contradictions. And this is, however, the gap that SHACL fills in the semantic technology stack. So we saw an example of OWL in combination with SHACL a few slides ago. And here are some more possibilities on how and when to use the different languages. Concept modeling. When you are to describe an ontology of abstract concepts, you could use OWL or SHACL, or you can use both. In my current project at the Norwegian Maritime Authorities, we use both in combination. One of the main reasons for that is that the NMA had OWL Lite ontologies written for their domain before I joined the project. I introduced them to SHACL and the modeling possibilities it provides, and we're going to see examples of the modeling possibilities a bit later on. Now we only use OWL for keeping track of the class hierarchy of concepts and their labels. So it's like a taxonomy. Yes, it's supposed to be on slide 21. Okay, SHACL is used for detailed modeling at the NMA, including data type constraints, modeling of alternatives in the regulation requirements, and more. If you have a lot of instance data, yes, sorry, I just lost myself a bit. If you have a lot of instance data, SHACL would be of great help in order to create a schema around this data. In a previous project, I worked with the library collection of the Oslo Public Library. This contained a lot of instance data: books, movies, persons, music, events, you name it. Much of this information was manually typed into a cataloging system by librarians in order to make sure they didn't provide us with typos or some really weird information. We created SHACL shapes that would check this. So no data in the collection database would contain any wrong information. And if you need inferencing on your data, you could go for OWL, but you could also go for SHACL, because SHACL actually provides you with the possibility of creating inferencing rules through the SHACL advanced features. Sadly, there is no open source engine or framework that supports these features yet, as the advanced features are described in a W3C draft and not yet standardized. And one fancy opportunity you get with inferencing in both SHACL and OWL is an inference loop. So theoretically, you could give the SHACL engine the result from the OWL engine and vice versa, until there are no more triples added to the result graph. And if you have a wonder of a knowledge graph with a lot of amazing T-box models and a lot of interesting ABox data, you could use both, as we did for the project I mentioned at the Norwegian Digitalization Agency. Okay, so now let's talk about the details of the SHACL core. The building blocks of SHACL is the shapes, and a SHACL shape is a collection of constraints for a given RDF resource. You have node shapes describing constraints on classes, and property shapes describing constraints on predicates and their object values. We're going to work with books, movies, and persons as examples today. I know you were promised SHACL and regulation models from NoCon's PR, but I'm going to cover this in my talk tomorrow at 12:40 Central European Time, but I'll slip in a sneak peek at the end of this lecture. The definition of a node shape is that it is a shape that is not the subject of a triple where path is the predicate. In this example, we see a node shape with one constraint on target class, which means that constraints to follow in this shape has to do with the class book. The definition of a property shape is that it is a shape that is the subject of a triple that has path as its predicate. In this example, we see a property shape containing a path on author. Every other constraint in this shape will be a constraint on this predicate and its object values. Good practice is to name your property shapes. You will see examples of property shapes described as blank nodes too. However, these cannot be reused other places in your RDF file as they are not named. Property shape does not need to be explicitly typed as property shape, since as long as it contains a SH path constraint, it is a property shape per definition. Here we see an example of node shape and property shape combined. We use the SH property resource to add property shapes onto a node shape. So if an instance of the class book has a predicate author, it's the constraints in the author shape that applies to that relationship and the object values of that relationship. So now let's walk through the constraints available in the SHACL Core constraints vocabulary before we start on our tasks. So I'm going to walk you through each category, and there will be examples on each slide as well. So first out is the value type constraints that let us constrain which classes, data types, and node kinds we are expecting to see in our data. Node kinds can be blank nodes, IRIs, and literals. In this example we see here, we have a node shape that targets the class book. So all constraints to follow are regarding instances of the class book. We have one property shape connected to our book shape. It says that instances of class book may have a relationship author to some instance of the class person. If we instead would like to have the author relationship pointing to a string, we could change the class constraint on person to be a data type constraint pointing to string instead. Next, we have constraints on cardinality and value ranges. Cardinality constraints tells us how many occurrences of a certain triple we expect. If the author constraint from our previous example had a constraint on max count 1 and min count 1, that would mean that the author relationship on a book is to appear once and only once. In addition to cardinality, we have min and max inclusive and exclusive, which gives us the possibility of defining ranges for our values. In the example we see here, we have a constraint on the predicate pages for a book, on max inclusive 10. This means that every book with a relationship to pages, pages to some number, that number must be 10 or larger. At my current project, we use these value range constraints extensively, as we need to describe scopes of boats larger than 8 meters, between 10 and 15 meters, smaller than 9 meters, and so on. There's a lot of different combinations. Okay, so we also have some string-based constraints, and I like fooling around with strings a lot. And in SHACL Core, they consist of min and max length of a string, regular expressions, checking for a specific language tag, or a constraint that there must be one unique tag per language for that string value. And in this example, we see a constraint on ISBN numbers using the pattern constraint. This regular expression is supposed to identify ISBN numbers as both ISBN 10 and ISBN 13, which is the two different ISBN standards. And be my guest on checking it out if you like. Next up, we have the property pair constraints. It gives us the possibility of checking the object value of two different resources. We can check for equality, disjointness, if a value is less than or equals to the other. Let's look at this example. Here we say that a person's death date must be less than or equals to the birth date. This means that no instances of person can have a death date that is before the birth date. So no persons can die before they're born. We actually got quite a few violations on this at the Oslo Public Library because of old typos from the cataloging cards that was to be typed into our cataloging system. And apart from the string-based constraints, logical constraints might be my absolute favorite. And these are much of the reason we chose SHACL for my current project at the Norwegian Maritime Authority. And I'll show you an example from that project at the end of the lecture of our use of these logical constraints. And the logical constraints are list-taking constraints that gives us the possibility to state things as negation, that something cannot form to a given shape, and constraints, where all values of the list must be fulfilled in order for the whole expression to be valid. And or constraints, where at least one of the values in the list must be fulfilled in order for the whole expression to be valid. At last, we have the x1 constraint, where exactly one of the values in the list must be fulfilled in order for the whole expression to be valid. An example with logical constraints is shown here. It says that any instance of person shall have at least one first name or at least one last name. Both is also fine, but at least one of them is required. Another example of OR constraints, and this is a funny one. I know that this might give some OWL ontologists a hard time sleeping at night, but it is possible to state that a predicate's range might be both an object value or a data type value. Object properties and data properties are disjoint classes in OWL, but not in SHACL. And at last, we have some shape-based constraint components. We have already seen property constraints around listing property shapes onto a node shape. The node constraint used for conforming to a node shape. For example, a node shape for authors might have a node constraint to a node shape describing persons, since authors are also persons. The group of other constraints that doesn't fit into any of the other categories consists of closed constraint, stating that the shape is complete, ignored properties, that is a list of properties to ignore, has value, which points to a specific object value, and the in constraint that states that the object value shall be a member of the given list. And here we see an example of both closed and ignored properties. If we close a shape, a SHACL engine will expect all predicates for that given data shape to be constrained. For this example, book, every predicate connected to some instance of book has to be constrained, even RDF type. We can ignore some of these properties by using the constrained ignore properties on the predicates we want to ignore by the SHACL engine. Like RDF type, for example. It's no point in constraining that, is it? So, a SHACL engine will take in two graphs as input, the shapes graph and the data graph. The engine will check if the data graph conforms to the shapes graph. And if it conforms true, everything is splendid, and we can go on with whatever we're doing further with the data. If the engine conforms false, a validation report is produced. And each instance of a validation report has exactly one value of SH conforms. SH conforms is true if and only if the SHACL engine did not produce any validation results, and false otherwise. If validation conforms false, a report will be produced containing an instance of SH validation results. And the validation result can be described using the validation result vocabulary. Here we can retrieve information about the node that caused the result, value of the path, and value node of the violated constraint. And that is the triple. We'll get information about the shape where the violation occurred, and information about the constraint components that caused the results. You could have even more details described in some parent validation results. And we also have some annotation property that we could give some message for the user or developer. And at last, we have the severity level of the violation. Default level is violation if nothing else is stated, which is also the strictest. The other severity levels provided with SHACL are info and warning, where info is the least strict. Other nice-to-know features in SHACL, which are not necessarily validating constraints. If you are to reuse shapes, it might be so that you don't need all shapes provided from the source. Then you have the possibility of deactivating shapes, so the SHACL engine will ignore the deactivated shapes and its constraints. Annotation properties like name and description helps on making your shapes readable and organized. Order can be used to arrange shapes in a given order for any purpose. This information can, for example, be used by an application in order to say something about the order of output information. At the Norwegian Maritime Authority, we use order to differentiate the different alternatives described in a requirement. You also have the option of setting a default value for your shape. And you also have possibility of checking whether your shapes are well formed or not according to the SHACL syntax rules and retrieve this information as a part of the validation results. In this lecture, you have only seen one path option in property shapes. I'm not going to demonstrate the other options, but it is good to know that there exist more options for this. So You have the possibility of stating inverse paths, sequence paths, alternative paths, and 0 or more paths. And beyond SHACL Core, I want to mention some features. We have SHACL Sparkle, that is Sparkle-based constraints that can be stated using the constraint Sparkle. This lets you create rules with writing Sparkle queries directly into the graph. This is actually a part of the W3C recommendation of SHACL as it is now. So this might be implemented in some solutions of SHACL. We also have the dash data shape vocabulary, which is an unofficial draft from June of 2020, which contains a collection of reusable extensions to SHACL. And at last, I have already mentioned the SHACL advanced features, which includes inferencing rules, among other things. And the SHACL advanced features are not yet part of the standard, and that is why there isn't any open source implementations available yet. Okay, and now we have gone through the SHACL Core constraint vocabulary. So I think we'll go over to demonstration and hands-on, so we can look at some code. But I see there is a couple of questions. So I will stop sharing my screen now so I can prepare the demonstration. So I think we can take a 2-minute break before we start on the demonstration, if that's okay. And I can also have a look at the questions during those 2 minutes. Okay, so I think the 2 minutes has passed. I can just quickly have a look at the Slack channel. Why is RDF type always shown as an ignored property? Because RDF type is, it's well defined, so everyone knows what RDF type is expecting to point to. It's expecting to point to anything that is a resource, or not a resource, but a class. And we don't bother to constrain it because of that. Therefore, we put it into ignored properties if we close a shape. When using SHACL closed, is it possible to reuse a node from another class? Actually, I don't know. I haven't tried it, but maybe you want to try it out when we go on to the tasks. And what are the dash data shapes vocabulary used for? Well, the dash data shapes vocabulary is a collection of shapes provided by Top Quadrant, really. And one of the employees at Top Quadrant is also one of the lead developers of the SHACL standard. So they have a lot of information and resources on SHACL that they want to share with anyone for reusing. I haven't had any use for the dash data shapes vocabulary yet, so I'm not that familiar with its content. I just know that it exists. But I have some links for the dash vocabulary at the end of my slide deck, so we can have a look at that when we do the summarizing after the tasks. Yes, thank you, Francois. Yes, the same reason for SHACL Advanced Features. And SHACL Advanced Features, I'm going to start working with next year, actually, so I'm really looking forward to that. And a quick overview of the advanced features. I think we can save that for after the tasks as well, because I want to eat time away from the tasks. Subclasses. Yes, and if I have a target class of event, how do I include the inferred subclasses like music event and theater event? That depends on the implementation of SHACL, actually. In the standard, it will do these kind of class inferencing automatically during the validation, so it will discover it, but it isn't the case that every existing SHACL implementation actually does that. But if you use the reference engine, which is located on GitHub, I suppose. I haven't been on that GitHub in a long time, so I don't know how it looks like now. But I can find the reference engine for you. And also like the SHACL engines that are supported by Stardog or any of the frameworks like RDF for Python or RDF for C# or RDF for Java, they will have some documentation connected to it describing what it supports and doesn't support. But in theory, you won't have to think about these kinds of inferencing. Okay, so let's go on to the demonstration. I hope the text is visible. Shall I enlarge the text further, or is it okay? There's nothing going on in the chat, so I think it's good. Okay, thank you, Gregory. Yes. So I have prepared some tasks for you, and you could choose if you would like to do this in Java, or if you would like to do this in the SHACL Playground. That is a browser-based validation engine for SHACL. Because I know there are plenty of people allergic to Java, but this is my main language, so I chose to do a demonstration in Java as well. And I'm going to use the RDF for J validation engine, that a good friend of mine has written. And let's have a look at how that works. So first, we have to initialize a SHACL repository. And here I initialize the validation report. And the model is the structure of a graph in the RDF4J and also in Jenna, which is the other well-known RDF framework for Java. And then we start the connection and we add our SHACL rules. So we have a reader here which reads a file of the SHACL shapes that I have over here. We're going to have a look at that quite soon. And we begin the connection and add our rules and commit them. And then we add the data shape onto our repository connection and commit them. And when we commit the data, we could possibly get a repository exception as in return. And if this repository exception is an instance of this SHACL sale validation exception, you will get the validation report from that exception as well as the cause of the exception. So we can return the validation report as a model and store it in the model we initialized at the beginning of this method. And I chose to write it to file, so we can have a look on the file as we go. And this implementation of the SHACL engine doesn't return a validation report with the statement conforms true. So I need to add that myself if I want it, but that's fine. So I do that at the end of this method. So if no exception was thrown, we will get conforms true. So let's, oh no, I completely forgot to show you the example from the Norwegian Maritime Authorities. Yes. Since I haven't started on the data here yet, I think I can slip in that now between the engine and the data examples. I'm so sorry about that. Okay, so here is a lot of stuff going on at once, but I'll try to talk you through it. So here is our subject of this shape, and NSD10. It's just our ID for a node shape for D10. And D10 is the certificate you need in order to become a sea captain in Norway. So in order to become a sea captain in Norway, you must be at least 20 years old, which this property shape is constraining. And you need this education with the code VD2. I'm not bothering to dip further into these property shapes right now, if that's okay. We will have a look at that tomorrow during my talk. And you will also need a medical course. And then we have this logical OR constraint that says that you need at least one of these courses in order to fulfill all requirements for this certificate. And then we have an AND constraint saying that you need the radio certificate and health certificate as a part of these requirements. And then we have the funny part, this OR constraint here, which describe the alternatives for this type of certificate, because you can either have a seagoing service with some parameters or another seagoing service with some parameters in order to achieve this certificate. So the first alternative is described as this AND constraint containing a list of certificates where one of these must be fulfilled in order to receive the sea captain certificate. And we also have some kind of seagoing service. And here is the order of 1 to state that this is the first alternative. The second alternative also contains some kind of or a list of certificates, where one of these certificates must be achieved in order to become a sea captain. And here we have 2 seagoing services as well. So you need both this seagoing service and this seagoing service. And this seagoing service is constrained even further in another node shape that is placed somewhere else that we're going to have a look on tomorrow. Yep. So because of the regulation texts in the Norwegian law text for maritime authorities, we needed this logical constraints and the combination of logical constraints, because the text contains of a lot of different alternatives in order to achieve different certificates. Okay, so that was the sneak peek of the regulation requirements. I'm sorry I forgot it before I started on this demonstration. Yes, so we have some data here that we're going to work with. I have added some taxonomy on the top just because I want to make the SHACL playground happy. And we also have 4 data. The words are disappearing, I'm so sorry, but we have 4 different instances of these classes here. The first is The Hobbit as a book with some title in English, a release date, pages, and an author. And the author Tolkien is an author, and he has some name. He's born on a certain date and he died on a certain date. And we also have the movie, An Unexpected Journey, which is based on The Hobbit, which with some title in English, release date, running time in minutes, and a director, Peter Jackson. And Peter Jackson is a director with some name, and he's born on a specific date. And the shape graph for these data looks like this. And it's kind of stusslig, as we say in Norway, but yeah, it's tiny. And that is because you're going to complete it. I found myself creating SHACL shapes based on existing data in almost every project I have worked with SHACL on. And that has been now 4 or 5 projects. So there is always some data available in the beginning that we want to use as a template for creating our SHACL shapes. And along the way, there might be changes in the data and there might be changes in the SHACL shapes, but the ultimate goal is to get a complete and sound schema for the data that uses the old data as a template, and for every new data that will arrive into the system, we have a sound schema to validate those data on. So I have created a public Git repository for this masterclass. Here you can find the slides, and you can also find the Java demonstration here. I shall probably show you how to run it. In main.java, you just run this validation. And we don't have any errors now, so that should go fine. Yep. And please extend the data.ttl and shapes.ttl file and only use those two files when working with the tasks. And these are pre-programmed into the validation code, and the SHACL playground that I will show you shortly also only accepts one file of each. And this ain't a large example either, so using one file is fine. So if I remove the title from the book, since we said that title shall be unique and mandatory, and run the validation again, we should have a validation report. Yes, we got the exception. And if we have a look at the report now, we see that it conforms false. And the validation result is considering the node the hobbit, and the constraint component is a min count constraint component, since we removed title and it expected at least one title. The source shape is title shape, and the result path is title. So we can look at the shape that says title should have a min count of 1. And we look at the data and see that the hobbit is missing a title. So it should be there. And that is how it looks like in the Java application. And if I bring this with me to the SHACL playground, that looks like this. If this, okay, the screen is updated. So before you start doing things on the SHACL playground, you probably want to switch over to turtle format here. And we copied the data first, so I'm going to paste that in here. And then I'm going to take the shapes and paste that in the shape graph view. And I'll run that, and we didn't get any report back because everything is fine. But if I then again remove the title that had a min count of 1 and update that, we will get a validation report that looks somewhat the same as the one in the Java application. The difference is that we here also get a result message. Yes. So the exercises you can find on this Slack GitHub repository. It's late in the evening for me, I'm so sorry. GitHub repository, my user, which is called Veleda / SHACL masterclass. So here are the slides, and here are the demo, the Java project I showed you. So you could choose if you want to use the Java application or in the SHACL playground, whatever you want. And the data folder contains the data file that I just showed you, and the shapes file I just shown you, and the exercises. So if you go here, you find the tasks. So first of all, you could try complete the shapes. That is already present. And then I have prepared some more data examples, ABox statements for music, games, myth, and opera. So you can extend the data file with this data if you like, and create SHACL constraints for that. So I put in some tips here and there in case users get stuck. Yeah, and we probably won't have time for the 2 last tasks, but yeah. feel free to play around, and I'll keep the link open, of course, if there is any questions, and feel free to contact on Slack, and I'll answer along the way. But I think I won't be talking for the next 40 minutes, so we can get some peace while working. But please open this discussion on the tasks on Slack, or if you want me to talk more about some subjects, please notify me on that as well. I'm going to go grab a coffee, and we'll have a 10-minute break before we start on the tasks. And I think we will set off. Yeah, let's gather again at 8:45 in my time. So that is in 40 minutes.
Great, thank you, Veronika, and see you all in a little while. Veronika, sorry, can you repeat the time you want to start back, or write it in the chat in case people have not?
Yeah, of course, I can write it, and also send a link to the Git repository.
Oh yeah, and if you could post that both in Slack and in the chat so that people who don't have access to Slack can still access it. Oh, thank you. Just, thank you.
I just want to check in and say that it's 5 minutes left of working with tasks. And if any of you want to volunteer to show your solutions, please let me know in the chat so we can give you the possibility of sharing your screen. Okay, I think we can do the summarization now. I hope everyone enjoyed the tasks, and I hope it wasn't too easy. So I haven't gotten any volunteers for showing their results, so I'll just show my answers for the tasks instead. That's okay? Yeah, let's have a look. Something like this, I suppose. There's a lot of data here. Not that much, but it's a lot of different kinds of classes with some few instances. So I've tried to cover every bit of the ABox examples I provided you. And you will rather look at the code, I suppose. So here we have all the data in one large file. So I just copy pasted in all the small snippets from the exercise folder into this data file. And let's have a look at the shapes. So first of all, I have chosen to split up the shapes in order to get my data more organized. So for example, for the book and title shape that we had as a start, we had the book shape that targeted the class book with some title shape. But when you look at all the ABox examples, you see that everything that is a subclass of work in some sort has the predicate title connected to it. So I chose to move title shape up to the work shape. And that is also the same for the relationship on release date. And in some of the ABox examples, we have title in several different languages. For example, the let me find it. For the myth of Edda, you have prose Edda in English and Den Yngre Edda in Norwegian. So I chose to put in a unique lang constraint on true, so that we could have different kinds of languages in the title. And I removed the max count of 1 and just kept the min count of 1. The release shape, here we did stumble across several kinds of data types. For example, for the book, we have a release date as XSD date. And for the game, we only have the year and not the date itself. So then I chose to put in an OR constraint that allows both XSD year and XSD date to be valid data types for the release predicate. The book shape then contains only properties on pages and author, because that is unique for instances of book in the ABox examples provided. And I also put in this node to work shape, so it inherits all property shapes described in work shape as well. The page shape is quite easy or simple. It's only a max count of 1 on the data type integer. The same for author. It's only a class constraint and a min count of 1, because I know, even though it isn't stated in these ABox examples, I know that a book can have more than 1 author. So I chose to remove or do not include a max count of 1 in this case. For persons, we have name, born and died, shapes, and author, director, poet, composer are all different kinds of persons. So here I have a typo. So here I chose to put in a node to person in every sub-shape. And the author, director, poet, and composer shape doesn't include any more property shapes because our ABox examples were quite simple, but they could include things that are unique for their specific class. So I wanted to divide them because of that. The name shape is a standard, unique, mandatory string. The born shape is much like the release shape because we encounter both year and date in our examples. Like for the myth here with Snorre Sturlason, he is born in 1179, but we don't know when in that year. And the death date is a complete date for this example for Snorre Sturlason. And a birth date would be unique and mandatory for every person in this example. And I also commented out here less than or equals to died because the RDF4J engine doesn't support property pair constraints, but the SHACL Playground, the browser-based validation engine, does that. So we could remove the comment and run it in SHACL Playground if you like. I'm going to push these answers to GitHub so you can have a look at it afterwards if you like. The dyed shape is much like the born shape, except from it doesn't include a min count one because we want to describe persons who are alive. So it would be a pity if everyone has to die before they are described. Like Peter Jackson, he's here somewhere. He is still alive, and therefore we want to only have the min, no, the max count, I mean, on one for dyed shape. Yes, the rest of the shapes are pretty straightforward, much on the same format that I have already described. Let's see if I have something more fancy here. Yes, developed by shape for the game. The game says it's developed by Beam Software, but we don't have any more information about what Beam Software is. So I chose to put on a node kind as an IRI for this predicate. So it only points to other kinds of objects, object values that are not literals. But I don't know what kind of class Beam Software is. My experience would tell me that Beam Software is a company, but it isn't stated here, so I won't make that assumption in the shape. The same for album by in the ABox statements about albums. It says here that Nightfall in Middle-earth is an album by Blind Guardian, which I know is a band or a music group, but I haven't stated it, or it isn't stated in the ABox data, so I won't make an assumption on that either. Yes, and that's it for the exercise, or at least the exercise number 2, which I suppose most of you ended with. if I'm not wrong. If anyone managed to complete everything, well done. And I hope, again, I hope it wasn't too easy. But anyways, if you would play more with this data, you could try look for a common relationship between all these entities and classes, because I chose these data for a reason, and everything is surrounded by Middle-earth, really, except from the opera, but the opera is inspired by the same source as what inspired Tolkien to create Middle-earth, which is the Norse poem collection of Edda. So if you have some spare time one evening and want to play around with it, please try to create a concept of influence and work that influence each other and concepts that influence each other, and try to create SHACL shapes for that. That would be really cool to see. Some suggestions on how to do that. Okay. That was everything I was planning to show you today. Here are some resources and references, and I also promised you to say some few words about the Dash data shapes vocabulary and the SHACL advanced features, so I can do that in the last 4 minutes. And before I do that, I want to go back to the shapes I just showed you, and let's have a look at this OR constraint that says that the predicate born can point to either a year or a date. These issues, or similar issues to this, can be done by using the Dash data shapes vocabulary, because it includes a collection of shapes that can let you do similar things like this. Not exactly for a year or dates, but they have an option for days or date time. So this is things containing in Dash. It's pre-written shapes that you can reuse to extend your own shapes. So here we have an OR on a Dash shape that is date or date time. So they have a similar approach to the one I had in my solution, only for date or date time, and shortened down when I can reference it like this. So the Dash is can be imported by OWL import at the beginning of your shapes graph. And Dash includes a string or length string and some other collections as well. And for the advanced features mainly contains of things that are familiar from SPARQL. Like we have exists, and we have filter shape, which can be seen as a SPARQL filter. Intersection, union, and minus are all familiar in SPARQL. Also distinct and count. And the count is a bit exciting to me, at least, because in the regulation requirements I'm working on, we have requirements that there shall exist at least one life vest for each person on board. So I can actually use the count to count the number of occurrences of a specific predicate in order to enrich another predicate. So I'm pretty excited to get to work with this advanced features next year to see if I can model my requirements even more detailed. Yep. We also have ask and select, offset, limit, order by, the typical SPARQL stuff. And now I see we have reached our limit. If you want to take the discussion further, I will be available on Slack for some more minutes before I go to bed. Otherwise, thank you for listening in. It was a great pleasure to talk to you. Thank you.